In the second video, I'm going to show you how to solve the problem we've come across in the first video by balancing our binary trees. Reminder, we've seen that a tree such as this one lost all of its interests. We can easily guess why, and we'd rather have this type of tree which is much more balanced. A little uglier, but more balanced. So here we can see that several nodes have one child. Sometimes they have two, and there's about the same number of elements on either sides. So the search time will always be optimal. The only disadvantage of this tree are that you'll have to struggle to balance it, as well as the insertion and removal will be a little longer. To balance it, we'll use what we call a red-black tree. I'll show you what it looks like in C. It looks like this. Moreover, we have an enum which defines the node's color, black or red. The structure is the same, but we've added the field color. There's an advantage in keeping the same structure. We'll be able to tell the compiler that our structure is a struct s_btree, and it'll reply, okay, no worries mate, I'll do it. So you'll be able to use all the traversal functions you've created for simple B trees. It'll spare you having to rewrite loads of code when the treatment is exactly the same and the structure is almost the same. That's called polymorphism. That's a pretty primary shape in C. We can do much more, but you'll discover that on your own. Why red? Why black? Let me explain with some theory. Red and black trees have several properties. The first is that the parent node, the tree's root, is black. The second is that all leaves, including those that are null, are empty leaves. They're also black, just like the root. Third property says that a red node only has black paths. Either they're both null, either they're real nodes but black, either a mix of both. You see the idea. The last property, the most interesting one, is that from whichever node of the tree the amount of black nodes crossed in distance between this node and the last leaf is the same for every leaf of this node. Basically, this means the tree is balanced. It's a bit hard to get. Now, the insertion. This we'll ask you to do as well as the removal. I'm only going to show you one case of insertion. For other cases, you can do your own research and figure it out, where it'll be explained much better and you'll find better arguments. I'm just going to show you a simple case of insertion, which requires two operations. You're going to use changing node color and tree rotation. Let me show you. To insert in a red-black binary tree, we first proceed to an insertion, like in a basic binary tree. So by dichotomy, in the diagram G means grandparents. It's the node's grandparent. P equals parents, U equals uncle, N is the node we've just inserted. The colors are in parenthesis, black or red. After having done our basic insertion, imagine we get this tree. The node is red because by default, all nodes are red. We can see that this tree doesn't respect the properties of red-black trees. The P is red and should have two black children, but only has one. The one that's null. The other is red. Let's proceed to something quite complicated. Because the uncle is black and the father is red. So let's do something to balance it. It's a particular case. There are 4 or 5 like this. So let's rotate the tree. We're going to rotate to the right around G. You may want to put on your seatbelts. Post-rotation, we get what's below. G is where U used to be with U still under it, because it's still a binary tree, and P is now above G. If you think about it, you'll notice that if I do this to my tree at the beginning, it'll still be valid. And we'll still be able to traverse it in depth. And it'll still be sorted. In the end, G is bigger than P, so we'll be able to move it. below on the right. And we happen to be in this case, but we're breaking the rules of red-black trees because the parent is red, not black. So let's proceed to a color change between P and G. It'll look like the following diagram. P is at the root of the tree, so it becomes black, and G becomes red. This way we have a balanced binary tree. Keep in mind that this is only the case of insertions. There are 4 or 5, I think, but you'll see for yourselves. Every time you make an insertion, you must check the tree recursively to make sure you haven't messed it up. For example, the fact that this one is black or red could infringe one of the properties, forcing you to make some changes. Normally, we get by with 2 rotations and 2 to 3 colors in worst case scenario. The other cases, you'll find them yourselves, as well as cases of removal. And to finish this video, I'm going to give you some advice. The first is for you to create a function which displays your tree. The first element and the 2 following ones, etc. I also advise you to display nodes that are null and to keep unfolding them. It will allow you to debug all your functions and check whether your insertion went well and if the tree is balanced. It takes time to code this, but it's quite practical. The second advice is to read thoroughly whatever you find on the internet. Binary trees are used a lot, and you'll find a lot of material on the subject, which would probably be clearer than this video and will surely help better. Good day.